But the thing I wanted to talk about was ether cleavage. So back in my day when we had West, we learned that ether cleavage would go from 3 to 1 to 2 as the order of reactivity for the nucleophile, but that is actually a lie. It's actually going to be 3 to 1 because the entire mechanism is SN1-like. So let me just point that out. So when you have an ether, what happens if you have acid catalyzed ether cleavage is that you have an acid and your oxygen is going to act as a nucleophile and it's going to go ahead and attack that acid. That makes the oxygen very electrophilic. And it's going to start to cleave itself from the rest of the carbon chain. So that's what makes it SN1-like, if you remember from his notes. I really don't want to draw this out again. It's going to look something like this with a partial positive on the more substituted side. So there's 2 carbons that the oxygen is attached to. You see this one and this one. Whichever is the more substituted side, the oxygen, after it gets attacked by the hydrogen, it's going to start to peel itself away from the more substituted carbon. And then you get that partial positive. So just know that the way you cleave an epoxide or an ether, a cyclic ether with an acid, with a nucleophile is going to be from the most substituted to the least substituted. I'm not sure if that made any sense. So when I re-upload the answer key, I'm going to draw it out and try to make it as clear as I can. But anyways, we started chapter 12 in class, so we'll start chapter 12 now. So chapter 12 is just redox reactions. And besides redox reactions, the entire core concept of this whole chapter is just nucleophilic addition to a carbonyl. So here we have a carbonyl. There is a dipole moment on carbonyls because this oxygen is electronegative, and the center carbon is electrophilic. This is why we get reactions with carbonyls. So when we do a substitute, when we do an addition reaction to one of these, we're just taking a nucleophile, and we know nucleophiles like to attack electrophiles. So that's exactly what happens. That's the general idea for this entire chapter. Now the reactivity of carbonyls is going to change. Do you remember what makes a carbonyl more or less reactive?
Like the least oxygens or least like competition, the more reactive?
Yeah, so the least competition. Yeah, so less steric hindrance definitely helps. Yeah, what is resonance? How does that affect it? Yes. So the whole idea between about the reactivity of carbonyls is how much of an electrophile it is. So how strong this delta positive at this carbon is going to be. The more positive that carbon is, the more willing it is to react. And basically, if you guys like NMR or want to relate stuff back to it, the more deshielded the carbon is going to be, the more reactive. I'll just write that. So what are a couple of things that can reduce the reactivity? What are a couple of things that can make the delta positive less positive? Yeah, we have what? Induction, and I think Sarah said the other one, which was yes. So the more induction you have and the more resonance you have, the less reactive the carbonyl is going to be. So knowing that, how would you rank these 4 carbonyls? And it's from most to least reactive. So what is the most, yeah?
The
the OH, like the aldehyde. Okay, this one is the most or least reactive. Yeah, the third one is closer. So it's not the most because it has two things. It has resonance with the oxygen. So the resonance between these two oxygens, it kind of forms like a shell around the carbonyl. So you're gonna get more electron density there, thanks to the really good resonance. And the shielding, the fact that there's electron density around that carbon makes it not want to react. Yes, the aldehyde is the most reactive. Why? Yeah, there's no resonance at all.
Whatever that means.
I don't even remember what that means.
So then two would be ketone.
Yes. So the reason that aldehyde is number one is because the hydrogen has like nothing to offer. If you have a carbon like a CH3, it has some electron density that you can induct up to the carbonyl. But if you have a hydrogen, it's not going to give anything to the carbonyl. It's just like sitting there useless. So that's why only one side is donating induction or is giving an inductive effect. And because we're only getting that dipole from one side, the delta positive is going to be stronger than something like the ketone, where you get it from both sides. So in both the aldehyde and the ketone, we don't have any resonance. We only have induction. And out of those two, the aldehyde has the weaker induction, so it's more reactive. So we have our first two. These first two are like as a category, much more reactive than these other two. So it's gonna be like aldehyde is greater than the ketone, which is much greater than the carboxylic acid and the ester. But out of the carboxylic and the carboxylic acid and the ester, which one do you think is gonna be more reactive? This one? I think they're actually roughly the same. Let me just check. Yeah, I think they're roughly the same amount of reactivity because you have both resonance and induction. So both that carboxylic acid and the ester has this really good resonance going on, which shields the carbonyl carbon. And it also has induction from the oxygen and the carbon. So overall, there's just a lot more electron density being donated to the central carbon. Yeah, I think Roche had the same thing, that they're roughly equal.
Being that there was an R group though, would that make it slightly less?
I thought that would make the resonance slightly less, but I think the worst resonance is made up for the fact that the R group donates density. I don't think that's official. Just that's my theory. You know, because I was going over this and I had the exact same thought. Okay, so now that we have that, let's apply the same principle to this problem. So here we're ranking the following carbonyls from most to least reactive again, except we have all ketones. Almost all ketones. So what do you think we're going to apply to find the most versus the least reactive? Resonance or induction? Yeah. And we're trying to find the most reactive. So what induction are we looking for? Or how much induction? We're looking for the most induction for the least reactive. So which carbonyl has the least amount of electron donating groups? Which has the least amount of atoms that can donate electron density? One, two, yes, this one. And if you're dealing with all hydrocarbons, you can basically just think which has the least steric hindrance, because it's going to be proportional. The more steric hindrance, the more induction you have. So what's the second most reactive? Yeah. And then the third? Yes. Six for the last one. Yes, my Roman numerals are horrible, so I have to like. And then between 1 and 3, which one is more reactive? 1, yeah. So it literally just goes in order of most stuff attached to the carbonyl, or least stuff attached to the carbonyl towards the most stuff. Okay, so now that we have our order of reactivity, we can actually start some reactions. So we can do an oxidation reaction versus a reduction. Do we remember what each of those is going to do?
Oxidation chooses electrons or protons. And I think of it as like gaining an oxygen bond also.
Yeah, that's exactly it. So it's going to lose hydrogens and add bonds to an oxygen. Okay, yeah, and which side is that going to be, left or right? Yeah, because we added an oxygen, we added another bond to oxygen, so it's oxidation. And then what about going towards the left? What's going on there?
Non-gaining hydrogen.
Yeah, we're losing bonds to oxygen and increasing our bonds or our number of hydrogens. So that's going to be, yeah. And that's it. I don't know about you guys, but I have like trauma from Gen Chem oxidation reduction reactions. So like when I got to this class, I was so grateful that this was all there was to it. So now that we have an oxidation reaction, we can have different levels of oxidation. We can go from a primary alcohol to an aldehyde, or we can take it all the way to a carbonyl. And we're gonna need a different strength of oxidizing reagent to do that. So if you start with a primary alcohol, you could either go to an aldehyde or you could go all the way to a carboxylic acid. If you go all the way to a carboxylic acid, you need a strong oxidizing reagent. If you just go to an aldehyde, it's gonna be weak. And then if you start with a secondary alcohol, the only thing you can get from that is a ketone. So no matter what reagent you use, you're only gonna get a ketone. Then if you use a tertiary alcohol, nothing happens to it. So we can only deal with primary and secondary. Yeah, depending on what reagent you use. So for the first one, what's happening? The oxidizing agent took it all the way to carboxylic acid, right? So is it going to be a strong one or a weak one? Yeah. And then for the second one, how far did we take the alcohol? Yeah, we only went to an aldehyde. So what strength of reagent are we using? Yeah. And for the last one, it's a secondary alcohol to a ketone. So what can we use? Yeah, we can use any.
Is it because you can use either because there's just one hydrogen that you can
Yeah,
take away regardless?
there's only one bond that you can replace.
Okay.
So now that we know what a strong versus a weak oxidizing agent does, let's learn what they are. So one I guess tip is that if it has more than 4 oxygens, it's going to be a strong oxidizing agent. So out of all of these up here, which has 4 or more oxygens?
Na2CO2O7.
Yeah. Anything else? And do we remember the special name for that one? For H2CrO4. I think it's called Jones reagent, but I'm not sure actually.
Yeah, you're right. Don't be-
Okay. So we have those two. What else? Yeah. And you're like, oh my God, it has 3 oxygens, it's not 4, but the one from the H2O counts. Another like dumb way I memorized it when I was taking the class was like, if there's a crow in the name, it's gonna be strong. So like all of these, every time I saw one of these, I just called it crow. I was like, oh, crow, it's strong oxidizing. Oh, and there's one that should be on here, but I forgot to add it. Okay, another one is KMNO4. The 4 oxygens, it's strong. But that only leaves like 2 for the weak oxidizing agents. So what do we have? Yeah. And then we have the DMSO thing.
Are we gonna see O3 at all?
Oh, I don't think so. If he didn't put it in his like notes, then no. So if you have crow or KMNO4, it's strong. If you have something that's not crow, then it's weak. Oh, also, I think the DMSO thing is called sworn oxidation. So those are the two nicknames you should know. I think like on an exam, he would be like, he'd give you a carbonyl and say, or an alcohol and be like, oh, we did sworn oxidation. What's the product? And then you'd have to know sworn is weak and Jones is strong. But now we have reduction. So just as a reminder, what happens during reduction? Yeah, you add a hydrogen. So there's two reducing agents. Do you guys remember which one's weak and which one's strong? Yeah. So let's talk about what each one can react with. So we have our aldehydes and ketones. Our aldehydes or ketones are going to be more or less reactive. Yeah. So knowing that, when you react an aldehyde with a reducing agent, is it going to be able to go all the way to a primary alcohol, or does it have to stop at a secondary alcohol? Yeah, it's going to go all the way to primary. And what about ketones?
Needs to be protonated.
It what?
It needs to be protonated.
They do need to be protonated, but could it form a primary or secondary alcohol? Yeah, only secondary because there's already two things attached to it. So. Okay, and now let's draw out the mechanism for this. So for aldehydes and ketones, you can use either reagent to reduce them all the way. Like you don't need a strong reducing reagent to bring an aldehyde to a primary alcohol. You can use anything and you'll get the same result. So let me just draw the mechanism and then you guys can do the other ones. So when you have a reducing agent, the actual reducing species that does the reduction is an H minus. So there's an H minus that's somewhere in this molecule that does the attack. The H minus is a pretty strong base and it's a nucleophile, and we have our electrophilic carbon. So it's just going to go ahead and attack there. Once it attacks there, the electrons from the pi bond, from the oxygen to the carbon, that gets shifted up as usual. And then we get this. Our oxygen has a negative charge on it. This stays the same. And then we get a new hydrogen. So after that, we have a nucleophilic oxygen. So we take an acid, we can be water or like H3O+, and it's just going to protonate itself because it wants to be stable. So we basically added two new hydrogens. The first one was from a nucleophilic addition, and the second one was from an acid-base reaction with the alkoxide that we made. And that's all. Remember, the whole point of this chapter is that you're adding stuff to the carbonyl. In this case, the stuff we added was the hydrogen. And then for a ketone, what do we think the mechanism is going to look like? It's going to be the exact same thing. So we have our H minus from this NABH4, goes in, does the attack. And then we get our two new hydrogens. Except in this case, when we were working with the aldehyde, we only had one R group attached to the carbonyl, so it only becomes a primary alcohol. When we have a ketone, we have these two R groups, so it's gonna stay as a secondary alcohol. Now this is gonna change when we have esters and carboxylic acids, because with those two functional groups, we have leaving groups. So with the presence of a leaving group, we can add more stuff to it. Now, do you remember, are esters and carboxylic acids are they more or less reactive? Yeah. So we need what kind of reducing agent to work on them? Mhm. And then do you remember what the reagent was for strong reduction?
Bro.
That was strong oxidation. Yeah.
Yeah.
Okay, and since we have a leaving group, we're basically just gonna treat it like, or think about it like an aldehyde. So there's two R groups that are technically attached to the ester, but since one of them is gonna leave, only one R group is retained. So when we react an ester with a reducing agent or a carboxylic acid with a reducing agent, since this half of it leaves, we can go all the way down to a primary alcohol. So instead of just adding one H minus to the carbonyl, we can add two H minuses, because in one case, it'll just remove one of these bonds with the oxygen, and in the second addition, it'll just remove this entire group. So let me draw the mechanism for that. Starts off the same, you get that attack. And you get your new hydrogen. But here's where it starts to be different. So we have these extra electrons on the oxygen. What happens is that these electrons come back down and reform the double bond with the carbon. So like this. And we can't have too many bonds on the carbon, like this is 5 bonds, so one of them has to leave. And the one that's most suited to leave is this OR group. So that just goes away. After that, we are left with an aldehyde. So now that we have an aldehyde, we can do the reaction again with the reducing reagent and add another H minus. So now we have two hydrogens that were nucleophilically added. And then we have our nucleophile with the alkoxide ion. So that's just gonna attack an acid and get protonated again. And we're done. So we retained that one R group from the beginning and we added these two hydrogens. The first one we added as a normal carbonyl addition to replace the double bond. And then the second one was added to replace the OR group, our leaving group. So you kind of reduce it down to an aldehyde first, and then you reduce it down to a primary alcohol. No, you can't do that with a ketone because hydrocarbon is like an atrocious leaving group. It's never going to leave. Yeah, because we have the oxygen here. The oxygen can hold the charge decently well, so it's willing to go. And then before we do it with the cyclic ester, just know it's the exact same thing for a carboxylic acid. It's the exact same mechanism, but except for an OR as the leaving group, we have an OH. I'll just draw that quickly. Yeah. So step 1 is to form the aldehyde after kicking off the leaving group. Step 2 is to just do another addition. And then after your second addition, then you're going to protonate the alcohol because it can't get reduced any further. That's all. And then if you have a cyclic ester, it's just the exact same mechanism, except you have to do some ring math. And then once the leaving group leaves, it still stays attached to the molecule, just not cyclically. So here's what that looks like. First you attack with your H minus. This opens up, and then you get your oxygen ion. And then this is going to come back and reform the double bond, which kicks off this group. So now we have an O minus over here. Now we have an aldehyde. So once we have that, we can reduce it again. So the H minus comes back, does another addition. And now we have a primary alcohol on that side. Oh, and then this just gets protonated. And then the last step is for this oxygen to also get protonated. And there's your final result. So because we got a cyclic ester, we're going to have 2 alcohols on the same molecule, and they're both going to be primary. And instead of like, oh, yeah, so in this step is where we'd have the acid, and then it would just protonate these 2.
In terms of like oxidation and reduction, would we ever see like deuterium thrown in there? Na4?
That's definitely possible. I don't think they're that creative, but it's possible.
Can you like show us?
Yeah.
Huh?
With deuterium, really? Wow, okay.
That would be the hell.
Okay. But yeah. Yeah, kind of. So the bond breaks, and then protonation is something that you just generally don't worry about when it happens. You just have to be aware that it happens at some point during the reaction. But for that, but for the oxygen to want to be protonated, that would have to happen after it opens up, because that's when it gets the electrons. Yes, because we can't have just two O minuses. We need to stabilize them. And that's why we have the acid underneath. One thing there's like a 0.5% chance he'll do this. It's like he won't include the acid, then you would know that it wouldn't get protonated. But they just like come as a pair, so I don't think you have to worry about that at all.
We wouldn't assume like it's just water.
Huh?
We wouldn't assume like-
Yeah, that's the other thing. I think it's safe to just assume everything gets protonated.
Yeah, he like really drilled it in class, like, does everyone understand how this gets protonated?
Really?
Yeah,
Oh my God.
yeah, like a student asked something, like, where does the H come from? And he like went over, he's like, does everyone understand that? Yeah.
What was I doing? Oh yeah, I was drawing it with deuterium. So let's just use this example. Let's take a carboxylic acid and use LiAlD4, I guess, over H3O plus. So we would do the same thing, except it would be D minus. So remember, first step is to just attach the hydrogen. And then in the second step, the double bond reforms and kicks off the leaving group. And then we get another D minus to come in and do the attack again. But instead of protonating this last oxygen with a D, we're going to protonate it with an H, because when we protonate it, it's coming from the acid. And this acid is H3O plus, not D3O plus. So we're just going to keep it as an OH. That's the only thing. If you ever get this question, it's the only thing you should be careful about. And that's all. So just know that the hydrogens that get added become whatever isotope you're using, and the hydrogen that you protonate with is going to be different since we're using a different reagent to protonate. Now we have these 4 practice problems, but they kind of like take forever to do, so I'm just going to skip those for today and we'll revisit it. But let's do this one. So which reagent would be used to perform the following transformation? So what's the transformation that's happening here? Yeah, we are reducing. But in this giant molecule, what functional group are we reducing into what? Yeah, the ketone into, yeah, and ketones can only go into secondary alcohols. But there's some more stuff in this molecule, right? Do we notice any non-hydrocarbon things in this mess down here? Yes, we have a CO2CH3. So what does a CO2CH3 indicate? A what? I'm sorry, I can't hear.
Ether.
Yeah, we have, wait, not ether. We have 2 oxygens, right? So one is going to be double bond as a carbonyl, and the other one is going to be doing what? It's just chilling with the CH3. So if we do this, it's going to look like this. Right? Because we have our central carbon, the C, then the 2 O's, and then the CH3. So it's an ester. And then, yeah, this is going to be a leaving group. And do we remember what kind of reagent we need to reduce an ester? Yeah. Is the ester reduced in this reaction?
No.
So what reagent do we know? What are we using? But LiAlH4 is a strong one. We can't use a strong one because the ester wasn't reduced. Yes. So we know we use NaBH4 because only the ketone was affected. All right, that made sense.
So that ester makes it more reactive, is what you're saying?
It doesn't make the whole molecule more reactive. You just need to know like what reagents are used to reduce what. So to reduce a ketone, we can use either strong or weak. To reduce an ester, we need a strong. In this reaction, we only reduced the ketone, so we know we had to use a weak one. Huh? I think like similar. Yeah. No, I think it should be more like this and less like the homework. The homework is, he gives you guys like really ridiculous stuff. So like you do hard problems and get good at it. But I think his tests are easier. At least it was like that last semester. I don't know how he's feeling this semester. Isn't that bad? No, his exams were not that bad last semester.
You have to use lockdown browser.
Yeah, but there's like a reason. It's really, really tough to cheat on his exams,
Well,
even
that's cheating.
without.
It's like look at your notes or looking at that.
Okay.
Is that cheating?